hope you have a great week. So today we are going to talk about our two milestones. So the first milestone, which we kind of spend the first part of today's lecture, is we are looking into how we can use a computer program like Python to compute the efficient frontier. Yeah, so the code snippets I have on the slides are complete. So if you take them into your own Python code, then it will run. And the second milestone for today is a fresh look into the capital asset pricing model. Yeah, kind of assuming you haven't heard about that before. We will start off with the Markowitz investor and see that the CAPM, which is a method, which is a theory basically, which tells us how expected returns should be determined in equilibrium. And that is a natural consequence of Markowitz investors. And both of these concepts were awarded with a Nobel Prize a few decades ago. Okay, but for now, we get to the milestone of seeing how we can implement the search for the efficient frontier in Python. And we will look at two examples. One is an unconstrained efficient frontier, and the other one is the constrained one. So in the unconstrained, the investor doesn't have any bounds on the portfolio holdings, while in the constrained one, we will put bounds around the portfolio weights. Good. Okay, now, so far we are in the intuition section, and we're going to finish this intuition part today. And already today you see that while we start off with the intuition to get an understanding of how things are behaving, once we bring it to software, it might be that the intuition-based formulas we've been using are too simplistic. And that is an example here for such a case. Because we cannot use there is a more elegant way relative to the MBA intuition equations we had last class. And that is what I want to go through today, because it will end up that if you see any type of software related to asset allocation, or if you program your own one, then it turns out for the minimum variance frontier that one can derive, and we will do that in a moment, a relationship between the portfolio holdings of an efficient portfolio, WP, and the target expected return, μP. And there's an affine relationship between these two. And that's what we're going to derive. And the G and the H, these loading functions, they will depend on the investment opportunity set. Yeah, so these are deterministic functions that later map every expected return that an investor would want to earn into what is the corresponding portfolio on the efficient frontier, or on the minimum variance frontier. And we will talk about today how to compute the minimum variance frontier, how to get the efficient frontier, how to get the capital allocation line. Okay, now for now we want to get a feeling on how this relationship is derived. And you see now the formulas are slightly more to what you're used to in your own studies. So let's just look into what we're doing here. We are basically now rewriting the Markowitz problem as Lagrangian. So L is our Lagrangian. It consists of an objective function. Here the objective function is the variance of our portfolio return. So sigma is the covariance matrix of all assets, and W is the portfolio vector. So therefore W is a column vector, so W transpose sigma W will be the variance of the return of my portfolio that consists of holdings W. It's convenient to put 1/2 in front of it. It will not change the solution. It's simply for convenience. Since we have a w square in the objective, that the square is then cancelling out with the half. We have seen that also in our MBA equations. And then we have lambda here, which is one Lagrange multiplier for the first constraint. And the first constraint is that we want our portfolio W to have an expected return, so W transpose mu, which coincides with the target expected return. Okay, and then we have nu. Nu is a second Lagrange multiplier, and it multiplies the constraint that all of our investments together, so if we add up the W's, so W transpose 1, it's simply the sum of our portfolio holdings, it has to add up to 100% to 1. Yeah? So we don't want to waste any funds, or said differently, we want to invest 100% of our funds into the risky assets. Okay, so therefore we have two constraints. These are two linear constraints, and we have our objective here. And the Lagrange multiplier is combining these, and we are seeing here that we want to minimize the Lagrangian. So we want to find a portfolio holding W so that the return variance is minimized, while at the same time these two constraints are fulfilled. Good. Then what one would do is we have here W. If we have n assets to invest into, then W would be n-dimensional. So it's an n times 1 column vector, which you also see here in my notation later on with the W index n, 1 to highlight it's a column vector. And then we have lambda and nu. These are two scalars. Each is one scalar. So we have n plus 2 variables that we want to solve for. And we see here that we will also have n plus 2 optimality conditions. So we get the optimality conditions by computing the first order derivative of the Lagrangian here with regard to W. That first order condition needs to be 0. And we also compute first order conditions with regard to lambda. And that is a typo in LaTeX. Sorry, it should be nu. This gamma here is nu. Didn't realize that before. And we also set that condition to 0. Now, I'm not explicitly solving that. I have some extra notes if you would like to see every step by yourself. For now, I just want to show you the objective function, the first order conditions, and then I tell you if you are solving now for W, lambda, and eta, and nu, so too many Greek letters, nu, then you're getting the solution in this red box, which I showed at the beginning of class. And that solution is telling me that the portfolio vector W, which is minimizing the variance, subject to earning an expected return of mu p, and subject to being fully invested in all the risky assets, fulfills such a fine relationship, yeah? Where G and H are functions of the investment opportunity set. So if we look at that, I've highlighted here in red what the G and the H looks like if you were to solve these optimality conditions. And you see both of them are divided by D. So what is D? D is here an extra expression, which is defined to be xz minus y square. So let's just have a look. What is x? What is z? What is y square? As I said, they just depend on the investment opportunity set. So let's just double check that we could really compute these terms. So the z depends on the covariance matrix of assets. It's inverted. Then 1 is the unit vector. So it's a vector with ones in its element. So we see here 1 transpose times sigma inverse times 1. So this will be a scalar. So at the end, z is a scalar. What about x? Also x depends only on the investment opportunity set. So it depends on the expected returns of our assets, the covariance matrix. Also that will be a scalar because mu is a column vector. So we have row vector times matrix times column vector will be a scalar. And y also depends on the investment opportunity set only. It will be mu transpose sigma inverse times the unit vector, so also y will be a scalar. So we will have z, x, y, as well as d will all be scalars. So therefore these terms here will be scalars, and you see that the g will be a column vector, because it has to be, since the w is a portfolio, or is a vector of portfolio weights, so w will be a n times 1 vector, and you see therefore also g has to be a column vector, and g will be a column vector. On the one hand, you see from here, you have something related to like the Sharpe ratio, sigma inverse times mu, so that will give us a column vector, and sigma minus 1 times the unit vector will also give us a column vector. Yeah, so the dimensions will be all right, and similarly for the h. So once again, what have we done and what do we want to do? What we have done is we have abstracted the problem more formally by really writing down the variance and the two constraints in form of a Lagrangian. We've been optimizing, but I'm not solving the optimality conditions. I just state what the solution looks like, and therefore we now know for any target expected return, we could tell the customer what the portfolio looks like that is on the mean variance frontier. The mean variance frontier is like this belly-shaped or these this bullet type parabola. We will see it has an efficient part on the top, inefficient part on the bottom. That's something we want to see. And our main objective now is to see how would we translate that into Python to generate a nice looking figure, which for all mu p that I might be interested in provides me with the WP. So the exercise is clear that we are going to do. Then let's just see how we do it. One more thing before we start. There is one special portfolio on the minimum variance frontier, and it's called the minimum variance portfolio. Sometimes it's also called the global minimum variance portfolio. Yeah. The reason for global is since every point on the minimum variance frontier is a minimum variance portfolio. So therefore, in the textbook, they might just call it the GMVP. And I'm stating you here the solution. And you see that for your own intuition, the portfolio which is fully invested in all the risky assets, but which has the lowest variance, does not depend on expected returns. That portfolio itself only depends on the covariance matrix of your investment opportunities. And one additional thought, if we did compute the portfolio for a minimum variance portfolio, we can now also compute its expected return and the return variance by using these two formulas, which we have seen before. So one would be W transpose mu. So mu are the expected returns of all the assets. W gives me the portfolio holdings that I invest into these different assets. So the product of both gives me then the expected return, and the variance of my portfolio will be W transpose times sigma times W. So it will also be a scalar. And you see how we nicely connect the investment opportunity implied covariance matrix with our portfolio holdings. Okay. Now, just to come back, to go a few loops to get everyone on board, the mu and the sigma, they are exogenous, as we say, yeah, because in Markowitz it's assumed they are known. And what is endogenous here is the decision variable, what the investor can affect, and that is the W here, the portfolio holding. Good. And it's exactly these formulas that I used in financial software. Now let's start with one example. So let's assume we have two assets. I kind of tried to mimic the picture from last class, from the textbook. Yeah, we had a bond fund D D stands for debt, and E is an equity fund. And I assume equity has an expected return of 8%. It has a standard deviation of 16%. This is also called the volatility of return A. And the debt fund has a 3% expected return. So already here we see there's a premium, an expected premium of 5%. But we also see that the debt fund has a lower volatility. Yeah, so the numbers are kind of realistic. And I'm assuming there's a correlation of 0.2 between returns of equity and returns of bonds of the debt fund. Keep in mind from last class, the correlation captures a linear dependence in prediction errors. Yeah, not in the means, but in the prediction errors. Okay, so therefore we kind of see that the debt fund will be a diversifier relative to an equity-only fund, because the correlation is pretty low. Yeah, from last class we saw there is a free lunch. If we start from the bond, 100% investment in the bond, we can increase the expected return in the portfolio if we add a little bit of the positive risk premium asset, but we also reduce risk because of correlation. But then there will be a point where risk is increasing. Okay, so if that is unclear, check back in the notes, but we also see pictures today, so there's a chance to catch up. Now what's the goal? The goal is first, we want to characterize the investment opportunity set. Then we want to find efficient portfolios. Here I call it WEF for efficient. And we will use target expected returns between 0 and 20%. And we also want to visualize the minimum variance frontier. Yeah, and that allows us to talk again about the minimum variance frontier, the efficient part, and how it relates to the investment opportunity set. So it's kind of a nice exercise to go catch up with what we have done so far. Okay, now, so I've been computing that in Python. So what I'm doing here, I'm importing NumPy, the package for numerical calculations. I call it NP. And later we want to plot the frontiers. So I'm importing matplotlib.pyplot and I call that PLT. Okay. Now what I'm now doing is now I'm translating the investment opportunity set into Python readable code. So I know that my equity expected return was 8%. The debt fund had a 3% expected return. So what I'm constructing here is a NumPy array. And the NumPy array will have a 2 times 1 shape. So that mimics the column vector, which I want to have for the mu. Now, you could change the order, right? You could have the bond fund first and equity last. You just need to keep in mind, basically, whether the first element is the equity or the bond fund. Yeah? But otherwise, the sorting doesn't matter, as long as you're then consistent. So I'm ordering here the equity first and bond second. Now, what I now want to do is I want to compute a covariance matrix, also part of the investment opportunity set. It will connect volatilities of the assets with its correlation in terms of the covariance. So that's what I'm doing here. You kind of see here I have 2 rows. This is row 1. There's a comma, then I have row 2. And the first and the last points across both rows, these are the elements of the main diagonal. So here I have 0.16, so 16% volatility for the equity fund to the power of 2, because everything is in terms of variance. And then the debt fund has a 4% vol. I square it, so it's 0.4 star 2. Yeah, in Python, the squaring, one way to do it is with 2 stars. And now I compute the covariance terms. You notice that the covariance matrix is symmetric. So whether you have the covariance of equity with bond or the covariance of bond with equity, it's the same. So you see these 2 elements here of diagonal are the same. So I have the volatility of the bond of equity, 16% vol, times 4% vol of the bond fund times the correlation. And that's the formula for covariance of equity and debt. and I use the same expression on the lower off-diagonal component. Yeah, here I'm giving you a printout, kind of anticipating you are recomputing that at home yourself, so you can double check that there's no typo. So that's what I've said here. The covariance is the same. Element, if we start counting in 0, so this would be 0, 0, 1, 1, this is 0, 1, and this is 1, 0. Yeah, these off-diagonal are the same. And here we have the variance terms. Okay. Now, relative to our case last class, not sure it was the case, or it was we had some example where the covariance was negative. So here you see it's positive. It's because the correlation is positive, 0.2. Yeah? So it sharpens your intuition that if the correlation was negative, also the off-diagonal elements would be negative, which is absolutely fine. Good. Now what we need to compute now is the vector of ones. So that's what we want to compute. And the way I do it here, I also assign a NumPy array to have dimension 2 by specifying I want element 0, 0 to be 1 and element 1, 0 to be also 1. Yeah, I can have the comma here is moving into the next row. And for readability, I like to call that capital I underscore 2. That's like in the English language, the capital I stands for identity. And if I do underscore 2, it reminds me it's a column vector of dimension 2. Because I, in mathematics, sometimes is also the identity matrix. Yeah, then I would call it I underscore 2 underscore 2, or I 2, 2. But here it's 2. I don't take 2 times 1 or something. I try to have minimal notation. But I2 kind of tells me it will be a 2-dimensional column vector. Okay. So I have my investment opportunity set now in the Python console, so I can now work with it. In order to work with it, I need an algorithm. That's why I've been introducing at the beginning of class the Lagrangian, which is the algorithm. We solve it analytically. Keep in mind, we account for 2 types of constraints. One is we want to meet the target expected return, and the other one is the full investment constraint. So it's not really constraints or what I called beginning of class bounds, but it's simply the 2 restrictions we always need. No waste, and we want to hit a target expected return. And for that simple problem, a quadratic objective function, variance, and these 2 linear constraints. Check again. What do I mean by that? I mean that you see these constraints are linear in our decision variable, while the objective is quadratic. So for that simple example, we can compute these analytical solutions, and now we're going to code them up. Yeah, that's also how you work in any type of scientific area, be it in industry or at university. You are explaining what the algorithm is doing. You verify the solution, or you cite a trusted source which did it, but still you should verify it, and then you're just coding it up. So here, that's kind of my template, and now I try to write code which uses notation which is mimicking the algorithm. Because if I mimic the algorithmic solution, it allows another person and me to find mistakes in my code easily. Yeah, and this is very important. You want, if there is a mistake in the code, and there will always be mistakes in codes, you want it to be easy to find that mistake. And one way to make it difficult to find a mistake is if you're coding using different notation than the algorithm that is underlying what you're coding. Right? So therefore it's good coding practice in all disciplines to stay close to the mathematical description. So if we look at that again, these are our mean variance portfolio weights. They depend on expected target returns, so we have to specify them exogenously. So we will have a grid. of expected returns that we care about. I said in the task for today, it's between 0 and 20%. I chose that because I see the max in the investment opportunity is 8%, so therefore I just go to 20. Yeah, you could go higher, but intuition already is if I go twice the length or twice the magnitude of the biggest expected return in the investment opportunities, that's already an extreme portfolio. So therefore I just went to 20%, otherwise there's no optimization behind that. G and H, I've mentioned before, it's the result of the optimization problem. So here are the proper definitions. Okay, here's one difference. The E, I said the I is used for the identity vector. Sometimes you also use the little e. The reason being is that capital I also stands for the matrix with ones on the main diagonal. So if I wanted to make the code especially nice, I would later define that in my algorithm the e will be in my Python code the I_2. Okay, but otherwise we have seen that before. Everything here will be scalars. And the scalar will be the outcome of matrix and vector multiplications. Okay, so otherwise, before we start, I also check, is there anything that could go wrong? Now, what can go wrong is matrix inversion. In our 2 times 2, that will work fine, because we only have two assets, so the sigma will be a well-defined matrix, but in a bigger setting, you want to make sure that you can invert the sigma. How to ensure, we can talk about that later, but I just want to mention these as warning flags. Otherwise, here we're dividing by d, so we should keep an eye that the d is not getting 0, because we don't want to divide by 0. Okay, but otherwise there's nothing that could lead to problems in the implementation. So let's then go step by step. Another thing for coding, you see that the sigma inverse is showing up in 1, 2, 3, 4, 5 computing steps. So what you want to do is, it's a repetition, you want to compute sigma to the -1 only once. It also applies to all other disciplines. If something is costly to compute and shows up several times, you're just computing it once. So here's what I'm doing. Also in terms of notation, you see how I call it. I call it sigma_inf. So it tells me, and hopefully the reader of the code, it's the sigma inverse. Yeah. I wouldn't call it inf_sigma, because the I goes to sigma first, so that it understands, oh, it's a covariance matrix. But then it goes to the index and sees, okay, I have to invert that thing. Good. So what I'm doing here is, within NumPy, there is a linear algebra package, and that package has a function, or has a method called inf. Yeah, so I put in the sigma, I compute the inverse. And here is what the inverted covariance looks like. Right? And you already see the covariance matrix. It doesn't look now that pretty anymore, because you already have now bigger discrepancies on the main diagonal. And the more columns you have, and the more a column becomes linearly dependent on the other columns, the more weird is such a matrix to look like. And in the worst case, the inversion will not exist if a column is closely to linearly dependent on the other columns. So what you could do in Python is you could write it down to yourself. In your notes, you can use pinf, that stands for the Penrose inverse. So it's an algorithm. What it basically does is it checks whether the eigenvalues are non-zero of sigma, because if they are non-zero, you can invert. And if they are 0, then it computes a new matrix, let's say sigma tilde, which is recomputed by ignoring the columns that correspond to a 0 eigenvalue. Yeah? And then it maps back to you the inverse of that matrix, and that's like a safe way to do it. You don't have to do it by hand anymore, because this the method exists in Python. Otherwise, we would have to do it ourselves. It's kind of 20 years ago. We would have used C++ or C, and there the library would not have had a safe inversion, so we would have to check ourselves what are the eigenvalues, set them, put the ones which are close to 0 away to shrink the matrix and the like. Yeah, but Python is very comfortable to use. It has many functions, methodologies. Okay, but in our case, it's a simple case, 2 times 1, 2 assets, so the sigma inversion is fine. Now the next thing we want to compute are now these x, y's, and z's. Yeah, so we look at the formula. X is mu transpose sigma inverse times mu, and that's exactly what we are translating here in the code. And you see how well we can compare what the code is doing relative what the algorithm tells us to do. So therefore, please always use notation very similar to the algorithm that is underlying your coding. So one way to do matrix and vector multiplication in Python is to use the at symbol. So mu was a column vector, now we transpose it, dot t, and then add sigma inverse. So now this is the row vector times the matrix. Then we are multiplying it by the column vector. Mathematically, that will be a 1 times 1. So it will be a scalar. But within Python, this is still a matrix or a vector, because we simply multiply a vector times a matrix and assign that to x. So for Python, this will still be a vector with dimension 1 times 1. But we want to give like a floating point number to x, and therefore we are saying dot item. And if you take dot item, parenthesis, nothing in there, it takes the 0th element. Yeah, again, in coding, the counting starts with 0. This is like in C, C++. I mentioned Python under the hood has C, C++. So therefore, if we take point item, now it really becomes a double or a floating point number. And that's what we want to have. Because I went through the algorithm and I saw x, y, z, these are all scalars. Yeah, so within Python, I need to enforce my x to be recognized as a scalar by this command here. Okay, so here's the solution. We do the same for y. We check y is mu transpose sigma inverse times the identity vector. So it's mu transpose alpha sigma inf times now my I underscore 2. My column vector with 2 elements, each being 1. Again, that would be a column vector with dimension 1 times 1, but I want a floating point number, so I say point item. And similarly for the z. Yeah, the z is E transpose sigma inverse E. Okay, so here's what I'm doing. I2 transpose times sigma inverse times I2, and then I take the point item to really force it to be now a scalar. So the z is just taken from my code. If I put z here, I get the output. Yeah, in case you wondered. Please.
Sorry, just one question. But is there like any reason why you don't use just a one-dimensional array for the mean and also the identity vector?
Well, it might work. You can check. For me, it's a matter of safety. I know that the d and the x, y, z's, they are all scalars. If I use a one-dimensional array, I don't know how Python does the implicit conversion in these calculations here. But I have the feeling, because Python is pretty advanced in this implicit conversion, that it will work. But for this teaching code, I want it to be as elementary as I can, and therefore I want to distinguish explicitly between what is really an array, here meaning like a column vector or a matrix. This is my mu and my sigma. It will also be my g and my h. And the scalars, I think about like doubles. I want them to be really just plain numbers, also within Python itself. Yeah? But it's a nice exercise to play around and to see. So you should always think about there are at least 5 ways to code up something. And I'm just presenting you one way. And here a way which mimics very closely the algorithm itself. Okay. And here I just want to mention the x I write down here is not part of the algorithm. It has just been used in order to compute the output. So that you could double check at home or wherever that you are on track with your calculations. Now the next thing I'm computing here is the d. So we had scalar times scalar minus scalar square. And now I'm implementing that as well. X times z minus y square, and I assign that to be the d. Yeah, so this is the value. And now I'm starting to compute these loadings, which then map my target expected return into the portfolio holdings. So one was G, and the other one is H. If we go back to the formula of G, okay, we divide by a scalar, D. Let's double check. I do that here in front of the big parenthesis, 1 over D. So D is a scalar. That's what I meant to the student previously. If D is still an array, I think the implicit conversion works, because Python does a lot of implicit conversions. But like me, I don't like implicit conversions. I like to be explicit. And this is very explicit because D is a scalar, so 1 over D is computable. And then what do we have in the parentheses? We have 2 terms, x sigma inverse e, and then y sigma inverse mu. Everything is known so far, so that should be now without typo here. X is a scalar, so I can simply use classical multiplication sign. These are matrix / vector, therefore I use the at for the multiplication. My output will be also a column vector, therefore I'm not converting. I just say take a vector, take a matrix times a column vector. It will be a column vector, and now the column vector is just scaled by a scalar by another scalar. Yeah, so it stays to be a column vector or an array, and you see it here. If I ask g.shape, it gives out it's a 2 times 1 array. So it's like my column vector, which I want. And here's the second part, which mimics the first one. Just the symbols are here different ones. And also for h, we have 1 over the scalar d, that z is a scalar. And whenever I multiply matrices and vectors, I use this alpha operator. Okay, so what we've done so far is we've put the investment opportunity set, mu sigma, into the code. We've been computing the mapping. In order to understand the mapping, you need to understand the algorithm. Therefore, I was mentioning where it comes from. And what we now want to do, now I go back 2, 3, 4 slides. We want to compute this expression here. Because we know for any expected return mu I, if I multiply by h and I add the g, I get portfolio holdings which are on the minimum variance frontier. Good. So the way to work with that is I'm going to discretize the range of expected returns. So here I use number of grid points. I take 400. There's no reason to take 400, so you can play around how many to take. The more points you have, the more the final picture will look like a continuous graph. But it will be still discontinuous because we are evaluating the algorithm at 400 individual points. So what I compute now is I compute the minimum expected return. So you also see in terms of notation. Yeah? I don't say expected return min, this is very long, but it's doable. But I stay close to the algorithm, which was mu, and therefore kind of like LaTeX notation for mu. And therefore to the reader who first goes through the algorithm and then through the code, it should be intuitive what the mu min stands for. But even though it's intuitive, you should always have an additional documentation, yeah? Either next or above, so that you and an external reader can understand what you aim to compute here. So here I'm saying min and max and increments for expected target returns. Okay, so I set the min to 0, the max to 20%, it's like in the exercise set, and then I compute the increments. So the increment will be the spread of the max and the min, and then I divide by n-1 steps, and that will really give me 400 points between 0 and 20%. And what I'm now computing, I kind of create, or I tell Python to create storage. And what do I want to store? I want to store the portfolio weights of these 400 different portfolios. And for each portfolio, I also want to store the expected return of the portfolio and the volatility. And now I'm assigning a storage to that, and I'm going to initialize these values with 0. There are different ways to do it. I just like to do it. It comes also from C. If you are creating a new object, you want to assign a value to it. Yeah? Because in C, it would just take any value which is in the storage of the machine, but I don't want that. I want to be explicit. So therefore, that's the logic of my coding. I'm therefore saying, first maybe I start from the inside. I want to generate an array which has number of columns mu.shape0. So mu is my column vector, 2 times 1. If I take shape, it goes towards the dimensions, and shape of 0, it says it goes to the first dimension, which are the rows. And since I have equity ordered first and then the bond, if I take mu.shape0, I will get a 2. And now I'm placing that after the comma, so it tells me I want 2 columns. And how many rows do I want? I want n rows, and n is 400. Yeah, so I want a 400 times 2 NumPy array. Also here you could change the order, but I think there's good reason to go with this order, but I can see you might want to change that. Just needs to be explicit and correct. And then you see what I'm doing here. I use the NumPy package, and there's a method called zeros. So if I call numpy.zeros, it will already compute an array with zeros in it, and here I'm just specifying the dimension. So if I now were to print out the w_mv, I would see it's a 400 times 2 array, and every element is 0. Good. Yeah, also notation-wise, the W is our notation for the portfolio vector. And now here I use capital MV to highlight it's the minimum variance. Therefore I know everything inside the WMV will be portfolios on the minimum variance frontier. Okay, now next thing, I want to compute the expected returns and the volatility of these MV portfolios. And again, I just create a storage and assign zeros to the values of it. So I will compute my routine for 400 target returns. I should say expected target returns, but sometimes I'm a bit short. I just didn't call it target. Although I try not to, because it's important to keep in mind it's about expected returns. So that should be a n times 1 array. I set every element to 0. And the volatility, you see also now, the sigma is small. That's like in math. In math, we would also make a small sigma to stand for the scalar. Capital sigma stand for the matrix, so I follow that here. So sigma underscore MV would also be an 400 times 1 NumPy array, and every element is initialized to be 0. So I think this is good practice to do. I also have some documentation on top. which is hopefully informative of what I'm trying to do here. So here it says I create objects to hold expected returns and standard deviation of minimum variance portfolios. Okay, so that seems to be all right. What I'm now going to do is I'm now going to loop through all these different target expected returns between 0 and 20%. One thing to keep in mind, if I compute the variance of a return on the minimum variance frontier, it's defined to be, as you would anticipate, you take the portfolio vector in my code, and in the algorithm, W is a column vector. So I would take W transpose. You also see here I used now the transpose sign instead of the capital T. So it's difficult to be 100% consistent throughout because I like the transpose sign more than the capital T. But sometimes I use capital T to highlight, or you will see in the Python code, .t is the transpose sign. So there we need to be a bit flexible. So we have W prime of W transpose times sigma times W. Good. And here's now what we do. We are now iterating through all target returns. We know from the algorithm, if I go back, we are now running through different values of mu I and then simply multiply them by h and add the g. Yeah, that's the step we are doing. And we know the first mu I we consider will be 0, the next one will be the increment, next one will be 2 times the increment, all the way up then to 20%. So the way one could code that is I make a for loop for I in range n. So that's a classical loop type in Python. In the modern C language, you can also use such a loop within C, yeah, but here in Python, this is very often done that way. So what you need to know if you see it for the first time is that if you have range of n, how to read that. Now n is an integer, it's 400. Yeah? And you have these round brackets. So it will basically mean that Python implicitly anticipates, and that's the way it acts, that the range you consider goes from 0, because in coding, keep in mind, counting starts in 0, up to n minus 1. Yeah? So if you go from 0 to 399, you have 400 entries. That's the way to be read here. Yeah? So for I in range 0 to n minus 1, so now I is the running variable. The first, once we enter the loop, then you have a double dot, and now we enter the loop. So the I will now be 0, and therefore I'm assigning the mu I, you see in the notation exactly like in the algorithm, mu I, not mu L, yeah, mu I, it's easy for the I to understand what I'm doing. It's I times the increment, so it will be 0. So now my target expected return is 0, and I want to compute the respective minimum variance portfolio. I call it Wi. G and H are known outside of the loop. And now I need to check dimensions. I know that, what do I know? G and H are column vectors. They were 2 times 1 arrays. And mu I is a scalar here. And therefore I simply use scalar multiplication. And I still will end up with an array. So Wi will be an array. Now I need to be careful. I've generated WMV previously in front of the loop to be n times 2. So basically for each I, this is what it says here, go to row 0. And now I want to have my portfolio vector as a row vector. This is not part of the algorithm, because in the algorithm I did not specify how did I store the Wi. Yeah? But here I need to store it. So therefore I made a decision n times 2. So therefore now I have to transpose my column vector to be a row vector. Therefore now I have a 1 times 2 array, and it gets copied into WMVI, comma, double dot. Yeah, double dot just kind of says whatever's on the right hand side, put that into these columns. Good. Now here I have mu mv, that's an n times 1 array, so therefore I simply call element I is 0, so it's the first element in the vector, and that should be a scalar, so here I take mu transpose times wi. Okay, keep in mind, the wi is my optimal portfolio. Optimal in terms of the Lagrangian, yeah, so it's the minimum variance portfolio that corresponds to an expected return of mu I. So I know that algorithmically my expected return on the portfolio should equal the expected target return, mu I. So I could either write the mu I directly in here, but it's safer because what could go wrong? Maybe in a bigger problem if we directly put the target expected return into this column vector here.
Either numerical instability, so the errors, or you make a mistake and the values you compute are false.
Yeah, so
it's better to use the one calculated in the model.
It could be that the constraint is not fulfilled. Yeah, it should be fulfilled because we've been solving the Lagrangian and it gives me the solution. So in these type of exercises, it will be fulfilled, but still, maybe it's a matter of preference. But I just like to go with the classical formulas that says the expected return of a portfolio equals the investment opportunity set implied column vector of expected returns, then I transpose it times the column vector of portfolio holdings. Yeah. In the analytics part, we had W transpose mu, gives you also the scalar, or here it is mu transpose W. So there are two ways to compute that. So therefore, I'm now computing the expected return of my portfolio Wi, and I assign that to be stored in here. And for the variance, I do some, for the volatility, you see, it's a little sigma, so it reminds me. Although I said variance, it's the volatility. Here's how I compute the volatility. I first compute the variance of portfolio W. Then I check dimensions. So W is a column vector, Wi. Transpose will be a row vector times sigma times Wi. So again, that thing will be a scalar, but the representation in Python is still that this is a vector. Therefore, we take dot item. Now we take out the 0th element of that vector. It's now treated as a floating point number. So now we have the variance. And now I want to take the square root, so I take star 0.5, yeah, to the power of 0.5, which is the square root. And that gets assigned to element I. And now the loop is over, so therefore the I gets incremented automatically because here it says for I in range. Yeah, so therefore Python knows if I'm at the end of the loop, it goes up again to check whether I is already outside of the range. But now in step number 2, I will still be smaller than 400. It will just be 2. And therefore you see what happens is now that is a local variable which gets created inside the loop. So it got already deleted if I go up into the for statement again. And now I have 2 times the increment will be my target return. And then I repeat the multiplications with the mu I, which is now by increment larger than the previous one. And that way, I'm walking up in discrete steps the y-axis, if you like. If you have to, on the y-axis, expected returns. On the x-axis, you have volatility. So I'm discretizing the y-axis. And for each point on the y-axis, analytically, I did compute the portfolio holding that minimizes the variance. And that's the way I compute it. So far, everyone is happy? Okay, great. Next thing, I do visualization. So maybe we look at the figure first, and then we go back to how I did that in the code. So here's now a visualization. I have sigma r, so I like to use LaTeX notation, yeah, so it's the volatility, but I put the r in addition to highlight for the student, it's the volatility of the return. And here I have the expected return. I could have called that also mu. And in dot, I have a legend here. It says individual assets. So the dot here has a lower expected return. So it will be my debt fund. This will be my equity fund. And everything on the blue line are portfolios on the minimum variance frontier. Yeah. You see now you need to use some intuition and some thinking graphically. The lower part of the minimum variance frontier contains inefficient portfolios. Because take, for example, this dot here, you have a vol of 0.1. The minimum variance frontier solution gives for 0.1 kind of two solutions. And I would, of course, like to choose this one here because I get higher expected return than down here. So therefore, the inefficient part is not of importance, so we would just ignore it. So we have to compute that ourselves in order to then focus on the efficient part, which is also called efficient frontier. Now, geometrically, the efficient frontier starts with the global minimum variance portfolio, which is slightly above the debt fund. So we have a bit of free lunch, and then it's on this concave shape here. Good. But we need to, if we compute the minimum variance frontier using this analytical algorithm, we cannot jump directly to the efficient part, but we need to compute first the minimum variance frontier and then compute the efficient part. There are two ways to get to the efficient part. I've mentioned one. I could find the global minimum variance portfolio, and then I know every other portfolio on the efficient frontier has an expected return which is larger. That would be one way to find. So yeah, I would say that's a classical way. I go back one slide, just see what we can learn in terms of Python. So the way I create the figure is first I say plt.figure. So it's like it kind of generates already a figure. It gives a storage to the figure. I specify the figure shall be called figure 1, and I give a fixed size of 12.7. Next thing I want to do is I want to compute in blue the minimum variance frontier. So I also provide a label to that. Yeah, I have a comma label. So label is a fixed word inside the plotting functionality, which Python understands whenever I write inside the plot function label equals and then high commas. That will be what is displayed over here in the legend. And what I'm plotting here is the x-axis first, so it's sigma mv. Sigma mv is known because I've defined it outside of the loop, and inside the loop I'm filling it up. And mu mv is also known from the loop. Yeah, so it takes now these 400 points, sigma and mu mv, and gives them a blue color. So therefore, although it looks continuous, these are 400 dots. Okay, what else do I do? Now I I keep working within the same picture. So I do plt.scatter. So now I want a scatter plot. So I want just dots. And what do I want to plot? I want to plot the investment opportunity set. So again, I plot x versus the y-axis. So the x will be the volatility of my investment opportunities. So therefore, I take the diagonal elements of the covariance matrix. So these will be the variance elements, and then to the power of 1/2. So I get the volatilities. And I plot that against the different entries of mu. And I want that to be black, the dots, and I label that to be the individual assets. You see from here, I cannot visualize the correlation, which is also part of the investment opportunity set. But in this two-dimensional graph, I just can't. So I need to keep in mind that also correlation is a risk factor, or it contributes to my risk description. Okay, so now I have plotted these two dots. And now I also provide axis description, so plt.xlabel and plt.ylabel. And you see you can use LaTeX notation and it will be understood in the labels. Okay, then I give a title, minimum variance frontier, unconstrained. Okay, then I say plt.legend, so it should use these labels in a legend, and then plt.show, it shall show the figure. Okay, so that's what I get here. Good. Now, next thing I want to draw is, I jump forward one slide. I want to draw here the capital allocation line. Yeah, that's what we have seen also last class. Now, what do we know about the capital allocation line? Who can share some characteristics? How does the capital allocation line, or geometrically, what do we know about it? Or anything you know about it? You want to say?
I think the intercept is the risk-free.
Right. That's a good point. So the intercept on the y-axis here will be the risk-free rate. Okay. What else? Please.
It has the highest possible slope for the tangents.
Right. So it's a straight line with a slope that is the maximum slope. How's the slope defined in this graph? The change in the y-axis over the change in the x-axis. So how did we call that in financial terms?
The Sharpe ratio?
That's a Sharpe ratio, yeah, because we have expected returns minus, as the colleague said, the risk-free rate. So it's the expected risk premium divided by the volatility, because the risk-free rate has a vol of 0. So we are really computing here the Sharpe ratio of risky assets, and as it was said by the other student, it's the steepest, or it's the largest Sharpe ratio possible. Therefore, we know that we are computing a tangent with the efficient frontier, or with the minimum variance frontier, but with the efficient frontier, because I don't want to have the tangent down here. Yeah. Therefore, I always say it an efficient frontier. So if I combine, for example, with the debt fund, you see my Sharpe ratio could be steeper. If I just go with equity, although it looks like equity is on the efficient frontier, I could still do better by really going and put up a straight line which touches the efficient frontier. And therefore, even though I want to take the risk of equity, if I'm moving along the allocation line, I get higher expected returns for the same amount of risk. So therefore, the allocation line, it starts at risk-free rate. It will have the largest Sharpe ratio, largest in terms of all the assets I could invest into. And we haven't computed expected returns down here because we directly were optimizing. And we therefore already know for each unit of risk, on the efficient frontier, we have the highest expected returns. although mathematically we've been computing it differently. Yeah? Mathematically, algorithmically, we've been computing for a given expected return, minimize the variance. But in my thinking, I toss away the lower part here, and therefore the efficient part, if I were to compute it differently, would really be for a given amount of risk, maximize expected return. So therefore the allocation line will have to touch the efficient frontier. It cannot move up here because it then relies on an allocation the market doesn't offer. And the efficient ones are on this blue line, right? So therefore I want to compute the allocation line. And here's an example now on how to do that. I need information about risk-free rate. Yeah, so it's also exogenous. So right now I just assume it to be 2%. So by convention, it would be annualized if nothing else is mentioned. So I have a 2% risk-free rate, annualized. And what I now compute, I will now compute the Sharpe ratio for every portfolio on the blue frontier, on the full minimum variance frontier. Now, I need to check that the mu and the sigma is also annualized, because I'm subtracting by RF, which I treat as annualized. How do I know it? I go back to the inputs. Yeah, 8% is also in annual terms. We have nowhere changed the units. So therefore, these are all annual numbers. Also 16%. We had the rule of thumb for market risk, roughly 20%, 0.2. Yeah, that's how I double check. These are all annual units here. So therefore, I compute directly an annualized Sharpe ratio. So I take the mu MV minus RF over sigma MV. So to the question of the student from a while ago, you see here also what happens is I have an array minus a scalar, which is fine, and then I simply divide also by an array. Mathematically, that's not really nice, but Python understands implicitly what I want, and it computes that element by element and assigns the values to a new array, which here I call SR for Sharpe ratio, and then underscore MV, which again highlights these are Sharpe ratios of my MV portfolios. So what I now have to do is, geometrically we discussed, I need to find the MV portfolio with the maximum Sharpe ratio. Yeah, so what I'm doing here is, therefore I first put up the comment, what am I trying to do? I want to find the portfolio with the maximum Sharpe ratio. And within NumPy, there is a method which is called argmax. So there it helps also from the formal training that we know that the argmax of an expression is the index which maximizes that, for which the expression is maximized. Yeah? Therefore, as an input to the method, I give in my Sharpe ratio MV vector, and I'm asking for which argument is that vector maximized, and it gives me back an integer because the indices go from 0 to 400, and I'm saving that argmax in TP underscore index. So you see the notation I'm using, TP, tangency portfolio, using the textbook-like notation. Yeah, the TP is the tangency point, tangency portfolio, and that's the index of it. So here I make a printout for you, and you see it's 91. So it means it's the 91st portfolio out of my 400. So it's in the lower fourth, in the lower 25th% of my expected returns. Good. So now I found the efficient portfolio that implies the highest Sharpe ratio, and that will be my tangency portfolio. And I know that the capital allocation line connects the risk-free rate with the expected return volatility coordinates of the tangency portfolio. Yeah. I found this point here, tangency portfolio, and now I'm simply connecting these 2 points with a straight line. Okay, but this comes next slide. Okay, so first I need to find the portfolio holdings of TP, because as of now I only found the index, so I know what is the target expected return that corresponds to this purple line, but I don't yet know the portfolio weights. Therefore I go into my portfolio weight matrix, WMV, and I'm evaluating that at row TP underscore index, so at position 91. And now I'm calling for the portfolio holdings, and these I assign to WTP. So WTP will now be a row vector, as you see here. So it says the tangency portfolio consists of 31% equity and 68% long-term debt, the debt fund. Both together should be 100%, because algorithmically we had the constraint in, and it looks like, that this looks like 100%. Okay, next thing, we want the coordinates in our two-dimensional graph. So what is the mu TP? I could either take the WTP and multiply by mu, or, which I prefer here, I've been doing the computation already, so now I simply get the expected return, which is a column vector, so therefore comma 0 I'm writing explicitly, I wouldn't have to. But I like to do it, just to highlight again, I'm really going for columns here, and I take element 91, or index 91. So the expected return would be 4.5%. You see, it's less than 8% for equity, but that's the beauty then of leveraging up, because I can move along the straight line here, according to theory, just by shorting the risk-free rate. So if I'm willing to take as much risk as my equity fund, I can still get higher expected returns, right? And efficiency in Markowitz, it's all about getting the max Sharpe ratio. And that is what we have computed. Then I compute the volatility also by getting the 91st element out of the column vector for sigma MV. And then I can compute the Sharpe ratio. So I know that the Sharpe ratio TP will be 0.415. Okay. So now I have everything I need in order to characterize the linear line in my figure. So that is what I'm doing here. So I also plt.figure1, so I kind of overwrite my old figure, shall have the same size that we talked about. It's my minimum variance frontier. I just changed the label a bit, make it shorter now, MVF, minimum variance frontier. Investment opportunities are also as discussed, and now what's new is my straight line. So I use a scatter plot. Not yet. I'm kind of decomposing my capital market line into a few steps. First step, like the student said, I highlight the intercept with the y-axis. So the x-coordinate will be 0, 0 vol, and the y-axis will be RF. That shall be a red dot, and the label should be risk-free rate. And then I also want this purple or violet color for the coordinates of my tangency portfolio, sigma TP versus mu TP. I call that then the TP portfolio. And now comes my line. So what I'm doing, I generate a local variable inside my figure function, which I call x, and that's with a numpy I take the method lin space, so it's a linear space between 0, which will here be related to the risk-free rate, and the max of sigma MV. Yeah, you could either just use numbers and make it fit, but what's nicer here is sigma MV is a vector, so therefore I take the biggest element of it, and this makes sure that the graph will match nicely with the x-axis. So now I have these points between 0 and the max sigma mv. And I know the capital allocation line is a linear line. It starts in RF, and then it has a slope of Sharpe ratio TP, and now multiplied by the increments on the x-axis that I'm looking at. Good. Okay, and this is how I generate this graph here. Yeah. Good. And now you could think about step number 2, asset allocation based on the risk aversion of the investor. The investor, or in our case the hospitals, they would position themselves somewhere on this allocation line based on their risk aversion. Yeah? They find their own point of tangency, or the way we saw it in the slides has been, we simply ask the hospital, what's your expected return you like, or what's the vol you like, and then we give them the position on the allocation line. Good. Now let's look at the example where I have some, it's in industry it's called constraints, but here mathematically we see the proper term would be bounds. I have bounds on my W entries. So we want to compute the minimum variance frontier and the efficient frontier with, and now I put some assumptions. I want that Wj for each asset j, so shall be non-zero. So I don't want to short one asset. So it's no shorting constraint, the jargon language. And I also want a diversification constraint, which in my example shall be that the Wj shall be not exceeding 50%. Yeah, so I want the minimum amount of diversification. And these two constraints are now used in one example with 3 assets to recompute what we've just done, but we cannot rely on the analytical Lagrangian, because if we were to add these constraints on the portfolio holdings, the analytical solution for the Lagrangian doesn't exist. So I have to solve it numerically now. And if we look at the solution already, we also see that whenever we are somewhere in this area, we could not compute any efficient portfolio which has a volatility greater than 40%, because in order to do so, what would need to happen? And why are we not allowed to do so? Anyone sees that from the graph already? If I wanted to go further up here, I argued in terms of vol. I can argue in terms of here, if I want volatilities of 16% and more. Oh, I'm so sorry. If I want expected returns of around 16% and more, there's no portfolio. And the reason being, I would have to invest more than 50% in this high risk premium asset, but it's forbidden by this constraint. So it gives a very nice intuition of why I cannot create a continuum of allocations, and that is the case we would anticipate to happen in industry, because I gave you arguments of why there are constraints in industry all the time in their portfolio allocation. And the same down here. Yeah? If you want a full investment portfolio, which has expected returns somewhere around 9%, that doesn't exist, because of the constraint that you can only invest less than 50% into this fund here, and obviously it seems you need more than 50% to go down here. Okay, but otherwise here we also nicely see diversification benefit. Instead of investing in that, we can do better by shuffling our funds across these 3 assets. So the example we are taking now is expected return 3%, 6, 8. These are my three assets. I'm kind of ordering that according to in ascending order. And they also have standard deviations 4, 13, and 16%. So the first one could easily be a bond fund, and the others could be two types of equity. And then we have correlation here, asset 1 and 2, 0.1. Then asset 1 and 3, 0.2. And 0.7, 2, and 3. So kind of the numbers mimic a little bit the example from the case study. We had foreign equity, domestic equity, and the long-term bond fund. Yeah, so you see also here a bit, I've mimicked these numbers here. That bond and equity, whether it's equity 3 or equity 2, has low correlation, and equity within itself has a higher correlation with each other. Good. So how do we compute that now in Python? The interesting thing is we can now numerically optimize. So we use the SciPy package for optimization. Otherwise, we use NumPy again and the plotting library. First thing we need is we need to translate the investment opportunities into the code. So we need the mu and the sigma. The way I've been doing it here, I write down what was given. Wait a minute. Oh, I see. The example doesn't fit this is because I've been playing around with, but I forgot to play around here. I will update the slides and then re-upload. You see what I've been doing here? The important thing is the code, but the code works with 12%, 18, and 8. Why? I copied from the wrong example. Here we had 3, 6, 8. So also the volatilities are different. Okay, so I will update this slide here with these numbers. Yeah? So we see I have sigma A 25%, sigma B is 50%, and sigma C is 7%. Okay, so I changed the example and forgot to update. So this one, sigma B, is like an individual stock, 50% vol, 25 is more like an index for equity, and this is more like a bond, long-term bond. Then I have correlations between AB, AC, and BC. So first thing I do is I compute my expected return vector. I use NumPy array, mu A, mu B, mu C. A, B, C, it's my ordering. For the full covariance matrix, you see here, I focused not on writing in the numbers, and therefore I think I overlooked to adjust the first number with the previous slide. But I wanted to show that here. I like that coding because it's easier for me to debug what I'm doing here. We talked about these commas, which give us different rows. So I see in red, these are my main diagonal elements. So it's sigma square A, sigma square B, sigma square C, which need to be known before I assign it in. So I've been writing it here a bit mathematical with double dot, so I just square all of these. And then I have my covariance terms, where I also wanted to use symmetry. So I have covariance AB, and I have covariance BA. So I compute covariance AB here, sigma A, sigma B times the correlation rho. And then for covariance BA, I simply assign covariance AB to be also covariance BA. And then I'm using it here. So that way I'm building up my covariance matrix. And what I now want to do is I now need to run an optimization. Good. Every optimization has an objective function. So therefore, what I'm doing here is I'm defining my objective function. The way it's done in Python, the definition of a function starts with def, yeah, for definition. Then you have a free space, and then comes the name that you assign to that function. Here I call it portfolio _variance. Yeah, so it's short and it's meaningful. And now in parentheses or in brackets, I have the input to the function, which is w. So again, it's short. It's meaningful because w is a portfolio vector, but I'm in addition add comments inside my function. You also know there are two dots here. That kind of tells Python whatever's coming after the dots is part of the function. And you see here we don't have curly brackets like in other languages, we simply have indentation. That is how Python knows everything here is inside the function. And if we were to start something here on the same level than def, Python knows it's outside of the definition. So here I'm defining for the reader what's the input, it's the W, what does it stand for, and what's the mathematical representation here. It's a NumPy array as a column vector. The output shall be a scalar, which the reader shall think about sigma p. And here I just give a note that in my computation I rely that the capital sigma is known. So it's like a global matrix. And what's the function really doing computation-wise? It takes the W and it multiplies that in with our sigmas that we talked about, takes dot item, so now it gives a scalar back, and that's returned. Good. Now here, what I consider good coding practice, you see that the function name is meaningful, portfolio variance. You could argue maybe I should call it portfolio return variance. That's all right, but on the other hand, it makes the title long, right? And we like to have short titles. You could make it very short, call it sigma square r. Yeah, it's a bit of your own preference. So far, I like portfolio variance. Then you see also that the notation here in the calculation, it follows the algorithm, which again is good coding practice in order to find mistakes easy. And you also see good coding practice is to have documentation inside the function. Okay, so we have 3 more minutes. So next thing, we are now computing the constraints. And we are also packaging the constraints in terms of functions. So we are now defining a new function, and I called it EQ underscore target return. So that shall highlight it's an equality constraint for the target return. So you see already I need to understand the algorithm here, otherwise the function name is not so meaningful to me. But I'm explaining again here what I'm doing. And in the return, I clearly see what the return is. It will be input W transpose mu. So that's the expected return of portfolio W. I take dot item, so now it's a scalar, and now I subtract from it the target expected return. That's why the node, the target expected return needs to be known. So it's like a global variable. It's not so nice for coding, but it's good enough for teaching code. I phrase it that way. So the mu target must be known before this function is called. Okay, good. And then I take another function for my full investment constraint. So I want that 100% of funds is invested in my 3 assets. So I call that EQ underscore full investment. So therefore I'm reminded it's the equality constraint for being fully invested. And it's going to return NP sum W. So W is a vector. NumPy sum is adding up these different elements in the vector, and then it subtracts 1 from it. And later, when we do an optimization with regard to these constraints, the optimizer knows the constraints have to hold in the optimal solutions. Good. So therefore, I'm defining here an object which I call constraints. And I use the notation that the SciPy package wants. And SciPy package wants that this is the language here of the package in high commas type, then double dot, then I can decide it's an equality or an inequality constraint. Here we work with an equality constraint. And then in high commas fun, SciPy wants the function, and now I'm assigning the function here, EQ underscore target return, which is this one here, and this one down there. The ordering doesn't matter, because both constraints will be tried to be fulfilled. So it doesn't matter which constraint I put in first. Okay, I think we stop here, and then after the break, we are going to continue.